There's an old rule that says you should start with what you know. This particular radio has two modulation modes. They are right here as AM and right here as FM. As we continue in the class, we'll see that each mode has certain advantages and disadvantages. AM, for instance, suffers from noise.
You're back. You're back.
And wore out, you need my help.
Whereas the FM stations are generally quite clear. So much for the receiver on my car, which is located somewhere over here. What we need is a receiver with a little more sophistication. And one place we can do that is to take a little trip. We'll take a trip all the way over to the Netherlands to the University of Twente. Somewhere on this campus, we are going to find a software-defined radio. A radio that looks like this. A radio that allows us to connect via internet. And here is what the radio receives. Now, like my car radio, it has different modulation methods. Continuous wave, lower sideband, and upper sideband, which is something we'll discuss, AM modulation, and the FM modulation. Let's start our exploration by going to a station known as the BBC4. Now, this is at 198 kilohertz, and it operates with an AM modulation. You see this symbol right here, this yellow piece? This is the tuning for the radio. This little bar right here is the center frequency that we're tuning to. So what we're going to do is we're going to set that right in the middle to where we see this brilliant band known as the carrier. From there, we can change what's known as the bandwidth of our receiver, which is by moving these filters here. You can think of it as goalposts. The bandwidth is the difference between the high frequency, right? That would be this frequency here, and the low frequency. And we can use this here to narrow the bandwidth, which gives us a sound like this.
Lucas, west by north 2, 5 miles, 1006.
Or a little bit wider.
Bridlington, west-northwest 2.
What you'll notice is when the bandwidth is set very narrow, you lose a lot of the information. You don't hear the sounds that the speaker is presenting.
Falling more slowly. Jersey, west 4, slight drift rain, 200 meters, 1013.
Again, this is BBC Radio 4. It's got a very wide bandwidth. Right next to it is another radio station. So let's see what that one sounds like. So it looks like we got some music there. We also have some interference. So what I want you to listen for is some raspy sounds in the upper registers. And watch this piece right here because it'll occur because the BBC4 and this station are right next to each other and they're walking over each other. So let's see if we can listen for that interference. It's fairly obnoxious sounding. What we're going to do is we're going to move this. So we're changing the bandwidth of our receiver, and I think you'll see that that interference is gone. No interference. Now we have interference. And now it should be gone. This particular type of display is known as a waterfall, and it shows time moving up, and the amplitude of the signal is the intensity. Again, I mentioned this piece right here, this brilliant band, is the carrier for the radio station. We'll talk about what carriers mean in the next couple of classes, but just know that right now it's a very intense signal. And then these things on either side of the carrier are known as the sidebands. In fact, that's one of the forms of modulation that we'll talk about in the near future. We'll talk about the lower sideband, which is all of these pieces. In fact, if I were to shift over to lower sideband modulation, you would see that the center is here and only the lower portion is accessible. And if I shifted to upper sideband, you can see it only uses the upper portion. But we'll get to that later. Okay, back to AM. Let's look at something a little more interesting. What we're going to do is we're going to go up into the amateur radio bands, and it looks like there's some activity here on 80 meters. We'll talk about the relationship between lambda, which is in meters, and the frequency in a moment. All right, so what do we got going on here? Okay, what's this one? Okay, those are all examples of Morse code. Remember that E is the most common letter in the English language, so E has the smallest character in Morse code. It's sent simply as a dip. If we move up the amateur bands a little bit, let's see if we can find some voice signals. Looks like this might be promising here. So we're going to go lower sideband. We're going to tune in right here and see what we get. Okay. You'll notice we're using the lower sideband modulation at this point. So here's the center frequency, this little bar here, and then we're looking at the lower portion right there. We'll see what this station is here. You'll notice that with lower sideband, it's critical that you get the tuning just right. Otherwise, they end up sounding like Donald Duck. And we'll talk about why that is as well. Here it looks like two people are having a conversation, but because of the way the radio reception is, we only see or can only hear one side of that conversation. These methods of modulation, continuous wave, lower sideband, upper sideband, AM, they're all examples of what are known as analog communications. Let's go down the band a little bit and see if we can find a digital method. If we move to this part of the band, we can hear what digital methods sound like. So that's one type. And if we move over here, it's yet a different type of digital modulation. While I can't say for certain, I suspect we are looking at military operators in this particular waterfall right now. We have computers talking to other computers, and with this type of communications, with a modem on each side, you're able to send text messages back and forth. As we finish up with this section, let's do a quick review. We talked about the frequency, the tuning of the receiver, which was this little bar right here. So we're going to set our center frequency to 198 kilohertz. We talked about the modulation methods. Most of what we looked at were analog methods, which is the first thing we're going to learn in this class. We did look at a few digital methods. Again, we'll get there. We talked about bandwidth, which is defined as the highest frequency minus the lowest frequency. So for this, whatever frequency this is right here, minus this frequency would be the bandwidth of the radio 4. We can change the bandwidth of our receiver. For example, we can make it very narrow, or we can make it very wide. And we also looked at the stations and where they are placed, and we addressed that, or cautioned that the stations can interfere with each other. And just because we're here, and just because I want to hear it, we're going to listen to the good old Loran radio navigation system. something that I spent decades of my life working on. We talked about Morse code. We mentioned the letter E. E is the most common letter, so it's going to have the shortest code. Letter T is also short. The letter I has some short codes too. So an E would be dit, a T would be da, an I would be dit dit. Other letters that are very uncommon or not often used have much longer codes. For example, Q looks like this, da 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 da. And J, there's another one, it's dit da da da. And this gets back to our conversation about information. Things that occur often should have very short codes. Let's take another look at our communications model. So here we are. Here's the microphone going to a transmitter, going to an antenna. Of course, that antenna broadcasts the signal and it goes to a receiver on the other side. And finally, in this case, we'll assume there's a loudspeaker where the other person can listen. Those modulation methods are a function of the transmitter. We addressed a few of them briefly. We talked about AM, not sure what it is yet, we'll get there. We talked about FM, talked about LSB, USB, I believe we also looked at CW. Whatever the transmitter is set to, the receiver must be also set to. For example, it wouldn't work if you had a transmitter broadcasting a lower sideband signal and a receiver set to receive an upper sideband signal. I'll leave it to you to go to that web SDR site and see what that sounds like. Horrible. Unintelligible. These were analog methods. There are also digital methods. And we did hear a few of those. One of them was the NATO-Stonig signal. For that system, instead of having a microphone, there's a computer and a computer. No mic, no loudspeaker, just computer to computer. The last thing, and I think everybody heard it, is that there's a large noise component out there in Radioland. Here's some terms that you should know. Simplex, that is a one-way broadcast. Half duplex, that's both directions, but only one at a time. You know you're talking on a duplex system when there's tendency to say, over. Right? That tells the other person that they can start. It's horrible radio practice, but you hear it all the time. Over. All right. Now, full duplex is both directions and at the same time. You perhaps own one of those devices. Mine is currently being charged. Right? Your cell phone is a perfect example of that. That's a full duplex receiver and transmitter. More terms. Analog. In analog signal, you could talk about a constantly varying voltage. So that could be a voltage, a current. My voice is analog, for example, as compared to digital, where things are either on or off. If we were to look in the time domain, for instance, using an oscilloscope, right, as a function of time, an analog signal might look like this. It's smooth, it's continuously varying, as opposed to a digital signal, which would have a discrete nature to it. It's either on or off. So analog or digital. Which one is better? Do you want analog or do you want digital? To answer that, I have to ask you a question. If you were to make a copy of a copy of a copy of a copy of a copy, how good would that version B. There was a movie back in 90-something that explored this. It was called Multiplicity. It was with Michael Keaton and Andie MacDowell. What happens is that the Keaton character makes a copy of himself. And that copy makes a copy, and so on and so forth. Copy of a copy of a copy of a copy. And you can imagine it didn't go so well because that last copy wasn't quite up to speed. It had lost something of the original. That's an example of analog. I don't know that that movie makes sense anymore because most of us are thinking in a digital mindset. And if you make a copy of a copy of a copy in the digital realm, you're left with the original, right? There is no degradation because the digital systems have mechanisms that allow you to clean up and preserve those signals, something that's just not possible in the analog domain. Again, more to follow on how that works. For example, if you have a compact disc with a scratch in it, most of the time it still works. And we'll explore why that is. Here's some more concepts that you should remember from the electronics class. If you have a sinusoid, we talk about the amplitude as a function of time. From here to here would be defined as a period. So the frequency is equal to 1 over the period, where the frequency is in hertz and the period is in, well, time. For example, our power line is a 60 hertz frequency, and the period is equal to 1 over 60. Right, that follows from this, doesn't it? So frequency is 1 over period. It must follow that period is equal to 1 over f, which gives us about 16.7 milliseconds. There's a whole pile of prefixes that you should commit to memory. For example, tera, capital T, 10 to the 12th, giga, mega, so capital G, capital M, 10 to the 9th, 10 to the 6th. Kilo is a K. Then there's unit itself. And from there, milli, small m, 10 to the negative 3. Micro with a mu, that's 10 to the negative 6. Nano, n, 10 to the negative 9. And pico, small p, 10 to the negative 12. Commit these to memory. They're going to be used again and again as we go through the class. You'll see them most certainly on every quiz and every exam. New term, and that is wavelength. So lambda is equal to c over f, where this is the wavelength. C is the speed of light, and f is the frequency. For example, one of the local radio stations is at 98.7 megahertz. What is the wavelength for that station? So lambda is equal to 300 times 10 to the 6th. By the way, that is the speed of light, so that's 300 times 10 to the 6th meters per second. Where were we? So it's speed of light divided by the frequency, and we said the frequency for that station was 98.7 times 10 to the 6th because it's megahertz. So our wavelength is about 3.04 meters. We'll make a quick note here that the antenna size is related to wavelength, and that's something we'll address in chapter 14. The textbook presents spectrum bands. You should commit some of these to memory. Certainly the voice band, which our author defines as 300 to 3000 hertz. Not to be confused with the limit of human hearing, which we'll describe as audio. For you folks interested in stereo equipment, that's defined as roughly 20 to 20,000 hertz. There's a very low frequency radio signal, that goes from about 9 to 30 kilohertz. And yes, there are radio frequencies that overlap the audio band because 9 kilohertz is in the audio band. These frequencies are of interest to military folks because the very low frequencies can actually penetrate the water, which would allow a submerged submarine to receive messages. HF, we'll describe that as 3 to about 30 megahertz. From there, VHF, you'll notice that's 30 to 300 megahertz. There's a lot of threes in here, and you'll notice that one band starts right after the other. UHF, from there we move into microwave bands, and even higher frequency we're into optics. Do spend some time with this section in the textbook and look for examples. For instance, your cell phone operates somewhere around the UHF band. We looked at bandwidth in our opening to this video, and we defined bandwidth as F2 minus F1. In that software-defined radio, we saw that frequency ran along the horizontal axis. Our bandwidth would be the width of this filter. So we can talk about an F2 minus an F1. As an example, if we went back and talked about voice frequency, so find bandwidth of voice frequency. B is equal to 3000 minus 300 hertz. That should be up here somewhere. Yep, there's voice frequency. So the F2 would be 3000 and F1 would be 300. So our bandwidth in this case is about 2700 hertz. As a sidebar, I want to point this out now. I think it's one of the most beautiful equations you're going to find in your textbook. It is something called the Shannon-Hartley theorem. You're going to have to wait a while because it's about halfway through the book. But it tells us that the capacity, which is how much information you can get across a channel, is related to the bandwidth, log base 2 of 1 plus the signal-to-noise ratio in the channel. This may not mean much to you now, but when we fill in all the gaps and we understand what this means, I think you'll find this to be a very remarkable equation. Again, this is the Shannon-Hartley theorem. As we finish up, let's take a look ahead to see where we're going next. So here is the microphone. Here's a person speaking into that microphone. The microphone goes to a transmitter. In that transmitter, we have a modulator. That modulator feeds an amplifier. And finally, the output of the amplifier heads to the antenna. Some terms we're going to learn very soon are the terms baseband. And we're going to talk about what the modulator is and how it works. We know some of the terms, for example, AM, that was an analog mode, FM, LSB, USB, right? Those were some of the terms we learned. And as we go along, we'll add even more complexity when we change the modulator from analog to digital. Once we get that far, we're one step away from understanding things like Bluetooth or wireless Ethernet.